Welcome back. Now that we covered and understood sampling in the previous segments, we address in this segment the change of sampling rate of a discrete signal. In many applications, we are interested in either increasing the number of samples in an image, referred to as upsampling or interpolation, or reducing the number of samples, referred to as downsampling or decimation. We analyze in this segment these operations in the discrete frequency domain. We see, for example, that downsampling introduces aliasing, and the way to minimize the effect of aliasing is to low-pass filter the image first with an appropriate filter before reducing its spatial resolution. Similarly, we show one of the possible ways to perform upsampling using discrete frequency domain filtering. Sampling rate conversion is an important operation with many applications, for example, in image and video compression. Multi-rate signal processing is an important sub-area of signal processing. The rate conversion in general can be performed by a non-integer factor. So we are touching the tip of the iceberg in some sense in this segment on this very important topic. Let us now proceed and look at the details. Sampling is an important topic, and it's taking us from the continuous world to the discrete world. Equally important is the process of resampling, or changing the sampling rate in the discrete world. It's often that we need to change the size of an image, either make it larger, upsample it, or smaller, downsample it. Although this is an interesting and rather broad topic that we'll be revisiting during the course, we want to mention a few ideas here as they relate to what we've been covering so far. Again, I will not be showing or deriving any equations, but pictorially provide some information of what's taking place. For those of you interested to look further into this, they can find this material in any standard book on image processing or one-dimensional digital signal processing. So, given an image, I'm interested in reducing its size by 2 in each direction. And here you see an 8 by 8 image. But I want to reduce it to a 4 by 4 image. We also show the spectrum of this image here. So this is 2 pi, and let's call this frequency omega 1 maximum in the one dimension, omega 2 maximum in the vertical direction. A simple or naive way to perform this downsampling is to remove every other column and every other row of the image as shown here. So therefore I end up with a 4 by 4 image. What happens in the frequency domain is shown here. The spectrum is squeezed down, the height is reduced. I of course don't show the height here, I just show the support. But also we see that the maximum frequency moves to this point in the horizontal and to this point in the vertical direction. So because of that, we see that aliasing occurs. High frequencies alias themselves as low frequencies, and this again manifests itself in the spatial domain in the form of jagged edges. So if this is my form of downsampling, throwing away, in other words, every other column and every other row, in order to avoid aliasing, I should be low-pass filtering the image before downsampling, and I should be low-pass filtering with a filter with cutoff frequencies pi over m in the one and pi over m in the other direction, where m is the downsampling factor. So you see an example here of the downsampling process we just described. The original image is a 4200 by 3000 pixels. It's too large, it's not shown here. And I show the result of downsampling with and without pre-filtering, pre-low-pass filtering. So on the left, you see the image that resulted by just, again, throwing away every 9 columns and every 9 rows, since the downsampling factor is 10 in this particular case. And the aliasing effect, as I already mentioned, manifests itself here. If we look at edges or high frequency components, we see that low and high frequencies are mixed up. It appears everywhere in this building. This is a picture of the Chicago skyline, while the flat regions, like the regions here, don't show any effect of aliasing as expected. On the right, I show the downsampled image to the same size as to the one on the left, but in this case, before downsampling, the image was low-pass filtered by a Gaussian filter of support 11 by 11 pixels, and the Gaussian means that the impulse response has some Gaussian shape within this region of support. So in this case, you see that the high frequencies are very well preserved. Of course, we lost some high frequencies due to the low-pass filtering, but we were able to preserve some of them. It's just, if you compare all kind of different regions here, you can easily see the difference. So let us see what is a way now for upsampling an image based on what we have learned so far. So we are shown here in this toy example a 4x4 image, and we are interested in turning it into an 8x8 image. We show the spectrum here of this image. So this is 2 pi, this is 2 pi in the vertical direction. The first step towards upsampling is to introduce columns and rows of zeros in between the existing samples. So clearly now I have an 8x8 image. What takes place in the frequency domain is that I see a frequency scaled version of the original spectrum. So I have a scaled replica of the original spectrum appear here at pi, another one at pi in this direction, and I only have one replica between 0 and 2 pi because the upsampling factor is equal to 2. All I'm interested in is keeping the baseband of the spectrum of the image, and I can do that by utilizing the low-pass filter indicated here. So what happens in the spatial domain is that I'm convolving the image with the inverse Fourier transform of this low-pass filter, which is referred to as the ideal low-pass interpolation filter. So the zero values that I have introduced will change now to specific values based on the existing neighboring pixels. Let us look at an upsampling example. An 128 by 128 image is shown here, and we would like to increase its resolution by a factor of 2 in both directions, so end up with a 256 by 256 image. We show here the spectrum of the image. It's a 256 by 256 spectrum, which was obtained by zero padding the original image to the 256 by 256 size. We want to show the spectrum so that they can see how it is altered after we follow the steps of upsampling. So the first step towards upsampling is to insert 0 columns and 0 rows to the original 128 by 128 image, so that the resulting image now is a 256 by 256 image. If I look at the spectrum of this image, I see these replicas of the baseband appear here. This is pi pi, for example, due to the insertion of zeros. The final step is to low-pass filter the spectrum so that I only keep the baseband while rejecting all other frequencies. So the blue areas here represent zero values. Now if I bring this back to the spatial domain, I see the interpolated image as shown here. An alternative way to upsample the image is to perform the convolution in the spatial domain with an interpolating filter like the one shown here. So this is the impulse response of the filter. This is the H00 point. So first of all, let's see what this filter is doing. So if I have in the low resolution image, let's say 4 values, A, B, C, D. As we saw, the first step is to introduce rows and columns of zeros. And the idea of the interpolation is to change these values of 0 to some other values. So if I perform the convolution again of this filter here with this image, we see that this 0 here will be replaced by A plus B over 2, this by B plus D over 2, while this pixel here will be replaced by A plus B plus C plus D divided by 4. I just take the impulse response of this, it's symmetric, so even I flip it around, it will stay the same, and I place the center at the pixel location. I try to find its value, and we see that this is indeed the case. Now what's happening in the frequency domain is that the spectrum of the low resolution, let's call it the 128 by 128 image, the 256 by 256 spectrum, which again we find by padding it with zeros as I showed earlier, is multiplied by the frequency response of the filter. And what's the frequency response of this one is, by now we should be able to look at it, and by observation we know that it's 1 plus cosine omega 1 plus cosine omega 2 plus 1/2 cosine omega 1 plus omega 2 plus 1/2 cosine omega 1 minus omega 2. So this filter, we showed actually the magnitude of this at an earlier point, how it looks like, is going to multiply the spectrum of the image, and this is the resulting spectrum of this upsampled image. So we see that what happens is exactly what I had before. In other words, this is a low-pass filter, so the replicas here in the middle of the spectrum are rejected, and I only keep just one replica of the spectrum at the baseband. However, now I'm not using a sharp low-pass filter as in the previous example, but the filter has the shape that is expressed by this equation here, right? H omega 1 omega 2, and it's depicted here as an image.
So this brings us to the end of the third week. By now, when we look at an image, we do not only see its bright and dark regions or its different colors, but we can distinguish between high and low spatial frequencies, regions where the intensity values transition in a fast way, or regions where they transition slowly, respectively. During this week, we learned that there exist computationally efficient ways, called fast Fourier transforms, that allow us to represent any given image in the discrete frequency domain, and therefore distinguish between high and low and intermediate frequencies. We also learned that we can now implement an LSI system, or perform filtering, in the discrete frequency domain. For filters with large support of their impulse response, this is indeed a much faster way to carry out filtering. We finally learned how the Fourier tools can help us in analyzing sampling or sampling rate conversion. The Fourier tools are of the most fundamental and useful tools one interested in working with discrete signals can get equipped with. They're actually the same tools whether we're interested in processing speech or audio, images, video, or videos of three-dimensional objects. I'm certain that the tools you acquired in these last 2 weeks will serve you well for the rest of your signal processing related careers. We will actually cover next week another tool, you might call it so, motion estimation, which is of the utmost usefulness when we process video. We'll also cover next week some of the fundamental notions of color image processing. So with that, I'll see you all next week.